Okay, so we're back. Some more discussion of the bootstrap. We saw an example of the bootstrap with the investments. And now, in general, we're going to talk about the bootstrap and think about it in more complex situations. So here's a schematic which I think is very useful. Actually, it's due to David Friedman at Berkeley. It's the real-world bootstrap world view of the bootstrap. So on the left, we have a cloud. And the ingredients, we're imagining, well, there's a population, a real population that gives our data, which I'm calling generically Z, observation Z1 through Zn. And from
these are like our training data, right?
Right, that's our training data. For example, in the investment example we just saw, this training data was a set of investments XY, X1, Y1 to X and Yn. Right, but we'll call that, going to call each of these pairs a Z. This is Z1 and up through Zn. So we imagined in that situation that we have our training data from a population of investments. This is in the real world, right? We have a training sample, and from that training sample, we derived a statistic, an estimate. In our particular case, it was the alpha hat, which is the proportion of investments, the optimal proportion of investments for X. So this is a summary, in the sense of what we did in the investment example for our training data. And what we wanted to get was an idea of the standard error of alpha hat. Now, and we made the point earlier that ideally, if we had access to the population, we could get more training data. We could simply grab more samples of training data from the population, more investments from the possible population investments.
You mean like a new sample, the same size?
Exactly, a new sample. And from the new sample, do the same analysis, get an estimate alpha hat, and do that many times. And we showed how you could do that on the computer in the previous example. But we made the point that not often can you actually do that in practice because you don't have access to the population. You can't get more training data typically. What you have to work with is just your given training sample. So the bootstrap, a way of thinking of the bootstrap in the abstract is say, well, we don't have access to the population. Let's replace the population, which we don't have, by p hat, which in the bootstrap's case is it's the training sample itself. It's a population that puts probability 1 over n being the sample size on each of the training points. So it says our guess for the population, which we don't have access to, but we have from a training sample, is if we have no more information, we're going to say with equal probability that a training point can come from the first point we saw, the second point we saw, up to the nth point we saw. So that's what we call p hat, the empirical distribution function. That's another name for that. Empirical distribution function. So when you draw from this empirical distribution function, that is sampling with replacement. And that's what the bootstrap does, right? It samples, we saw that. We draw samples with replacement from the training sample. That's this random sampling here, p hat giving z star. This is now the bootstrap sample. Remember, we're going to use a superscript star to indicate a bootstrap sample, as distinct from a training sample, which has no superscript. So this is one bootstrap draw. This is a sample of size n from our training sample now, a bootstrap sample, giving us the bootstrap data. And from that, we derive the estimate. Again, in this case, it's alpha, and we'll call it alpha hat star. So bootstrap sampling simply repeats this operation a few hundred times, say. For each time we get a bootstrap sample of size n, and we get a bootstrap quantity alpha hat star. And then the standard error of alpha hat star is the bootstrap estimate of standard error of alpha hat. So there's nothing new here. We're simply describing what we already saw in more general terms. Okay, but we can now think about how we would carry this out in more complex situations. So in general, we need to figure out how we can carry out bootstrap sampling. For example, suppose we have a time series. So let's draw the time axis here. And we have a series, like, for example, stock price. And let's just draw some imaginary data, right? Okay. So this is let's call it Y1. This is stock price at time 1, stock price at time 2, etc. And we want, for example, to predict the stock price from a given day, from the previous day's stock price. So we'll fit a model, a regression model, like we've seen, to each stock price as a function of the stock price in the previous day. Well, that's fine. We can do that. We can do that by least squares. But now we might imagine doing bootstrap sampling the way we just described, where we sample with replacement from the data. Well, one problem with that, that's a significant problem, is that the data are not independent, right? There's correlation in the time series. We expect the stock price for a given day to be correlated with the stock price from the previous day. As a matter of fact, if we're trying to predict the stock price from a given day from the previous day, we hope there's correlation. If they were independent, the prediction wouldn't be very useful. But this creates a problem for the bootstrap, because in the schematic, we were sampling here, or we assume that the sampling was IID from the population. Right? But in this situation, that's not a reasonable assumption, because the observations are not independent. So in general, when you set up the bootstrap and arrange for the sampling, you must figure out what parts of the data are independent. So one thing people do in a time series, because the observations are not independent, they're correlated across time, is to use what's called the block bootstrap. And the block bootstrap divides the data up into blocks, and between blocks, one assumes that things are independent. My spelling's not good. Okay, so for example, if we use a block size of 3, these would be the first block, these 3 observations, these 3 would be the second block, these would be the next block. And now our sampling units are not the individual observations, but the entire blocks. So we would sample with replacement from all the blocks, and then paste them together into a new time series. In other words, if this guy's sampled, he might become the first block, second block, etc. And then we paste them together in order, and that becomes a bootstrap sample, to which we apply the estimate, in this case, a regression model. So the point is, you have to sample the things that are uncorrelated. You have to arrange for, or find the parts of the data that are uncorrelated, and use that as the basis for bootstrap sampling. In this case, we use a block of size 3 under the assumption that beyond a time lag of 3, things are somewhat uncorrelated. But within a block, we expect correlation. So we keep the blocks intact, sample them as units. That's called the block bootstrap. I say that here, okay. So we talked about the bootstrap for standard errors, and that's the main use of the bootstrap is to estimate the standard errors of an estimate, like the alpha hat in our investment example. Another very common use of the bootstrap is for a confidence interval. So let's go back to confidence interval for a parameter. Let's go back to slide 29. And remember, this is the histogram we got from the bootstrap for the values of alpha hat over bootstrap sampling, 1,000 bootstrap samples. And if you look at this histogram, a reasonable way to derive a confidence interval is to take the percentiles from this histogram. Like suppose I want a 0.9 confidence interval so that it contains the true value with probably 90%. It makes sense to grab the 5th and 95th percent quantiles. So let's find the 5% point of this histogram and the 95% point of that histogram. There's 1,000 points here, so actually the 5% point would be the 50th biggest and 9/50th biggest value of alpha.
I mean, smallest and biggest.
Say that wrong?
You said it wrong. I didn't say it.
Okay.
I'm sure they understood.
It's okay.
Just like I did.
Okay. So if we do that, that provides a confidence interval for alpha. And what do we actually get? I've got that back on the slide I was at. So 0.43 and 0.72. So this is actually an appropriate confidence interval for alpha. And remember, how to interpret this confidence interval. What this means is that if we were to repeat this experiment from the population many times, it would be the case that the confidence interval that we obtain would contain the true value of alpha 90% of the time. That's what a 90% confidence interval is. We talked about that earlier. This particular way of constructing an interval is called a bootstrap percentile interval. And there's actually an entire field in statistics to do with confidence intervals in the bootstrap. And there's many papers and books that have written about this topic. This bootstrap percentile interval is the simplest way of constructing a confidence interval from the bootstrap, and it's very useful. We just use the histogram of bootstrap values themselves and use their percentiles. So we talked about the bootstrap for standard errors and confidence intervals. How about prediction error, like misclassification error we've seen in the course already? Well, the major tool we talked about for that was cross-validation. And let's think back at cross-validation, how it worked. We have k-folds in k-fold cross-validation. We divide the data up into k parts, let's say 5, and I'll just draw this again. And remember what we did, here's our 5 parts created at random. K-fold cross-validation, it's like, remember, like a 5-act play if K is 5. At one stage of the play, these 4 are the training set, these 4 parts, and the remaining 5th part is the validations part set. And cross-validation fits to the 4 parts, fits a model, and then uses that model to predict the 5th part. And then, and in turn, we then, this guy gets to play the role of the validation set in the next stage, and this guy, etc. And there's just 5 stages. But a crucial part of cross-validation was that when we do one stage like this, there's no overlap between the training set and the validation set. In other words, the observations in one do not appear in the other. And that's important because we're trying to get an idea of test set error on new data. So cross-validation is taking a piece of data, separating it out from the training set, so that when I fit on this data and predict on this data is in a sense new. It hasn't been seen by the model trained on the first 4. So there's a separation, a clean separation between training and validation. Well, what if we were to try to use the bootstrap to estimate prediction error? Let's just draw, again, the bootstrap sampling process. Here's my training set. And I'm going to draw samples with replacement from the training set, bootstrap samples, each one of the same size and a few hundred of them. Well, the first kind of obvious idea is to say, well, let's train on a bootstrap data set and then predict the original training set as my validation set. I can do that for each bootstrap sample. Each bootstrap sample gets to play the role of the training set to fit, and then I'm going to predict my original training sample as my validation set. Well, there's a big problem with that. And the problem is there's an overlap between the bootstrap data sets and the original data set. In particular, about 2/3 of the original data points appear in each bootstrap sample. And you should think about how to prove this. It's not hard, but you'll find out that about 2/3 of these points, so of the training set points, are in the bootstrap sample. This creates a problem because now I train here and then I do the prediction of the training set, 2/3 of the points in this training set have already been seen by the model because they're in the bootstrap data set. So on average, this 2/3 overlap means that most of the training points are not novel. So this is a big problem because the prediction error from this process will be biased downward. It'll be a lot lower than the actual prediction error because I'm predicting 2/3 of the points I'm predicting I've already seen in the bootstrap data set. So this is not a good way of estimating prediction error. Okay, they say that it underestimates the true prediction error quite dramatically. Now, you can think about the other way around. You could train on the training set and use the bootstrap samples as the validation sets, and that's even worse. And you can think about why that is. So it's even worse in the sense it's going to be even more biased. Well, how do you fix this problem? You can fix it by when you train on the bootstrap sample and then predict the training sample, just recording the predictions for the points that did not occur in the bootstrap sample. In other words, the points that are actually novel points. But then this gets quite complicated, and in the end, it's really not worth it. If you push this idea to its conclusion, you can get something which is about as good as cross-validation, but it's much more complicated. So our view is for this particular problem, the cross-validation is easier and better and the thing we recommend.
If I can just interrupt, Rob, that actually brings up an interesting point. A lot of the time, we have simple methods, like cross-validation, and then a new method comes along, like using Bootstrap to estimate prediction error. And we see it's quite a lot more complicated, and you don't get much in return. And so our general philosophy is, if you can get the job done with a simple method, it's far better than using a more complicated method, just because it maybe looks sexy or whatever. So keep it simple. That's the idea.